All right, so good morning, everyone. Welcome to our final day, which turns out to be quite a sprint. So maybe we'll just get started right away. So it's my pleasure to have Bertel kick it off today with the estimation for static games.
Okay. Yes. So so welcome back, and good morning. Good morning. What a beautiful day. It's about static games today. Let's take it away. So we're going to start actually with static games, the simplest possible static game I can think of, which is kind of like a simple exit entry game, and just then, illustrate a bunch of different estimation methods how you estimate those games. Okay, so I'm not kind of here to teach you about how to estimate static games. It's more about illustrating many of the problems that arise when you have games with multiplicity of equilibria. Right? And it's going to kick it off to Fedor, who's going to talk about solution of dynamic games, also a little bit about estimation of dynamic games of particular kind, and how that's all the more difficult when there's multiple equilibria. So here we have a very simple model where there's a very small set of equilibria. Okay, so it's not super responsive. Okay, so I'm going to try to go through here some of the different methods we heard about during this week: nested fixed point algorithm, the mathematical programming with equilibrium constraints, and the CCP type of estimators, and then also the nested pseudo likelihood, which is kind of like this sequential improvement of the CCP type estimators, where you plug back in the CCPs that you've just estimated, those predicted from the model, and that's apparently is going to be more efficient. So for games, it can be a little bit more dodgy because you have to worry about whether this stuff converges and so on. I'm going to take the simple example of a very simple static entry model, and then the explicit focus is going to be about multiplicity of equilibria. And then afterwards, we're going to talk about a dynamic model, Bertrand price competition, and with cost reducing investment. That's what Fedor's going to talk about. And there you'll see this huge multiplicity of equilibria because of the combination of all the many things that can happen in different states of the world. Okay. Anyway, so he'll talk about how to solve and find all those marker perfect equilibria. It is indeed possible, but you need like special tools. Okay, and then maybe a little bit about how to do the estimation. Okay. Okay, so actually, I'm going to kind of skip this literature, but there's some references here, and just go right to the example. Okay, so we're going to consider here two firms, A and B, okay, and they decide whether or not to enter the market. So you got two, binary indicators. They're the decisions. So that's this one for firm A, and then this one for firm B. Okay, it's one if you enter, it's 0 if you're not entering the market. Okay, and these two firms, they get some exposed payoffs depending on whether or not they enter. Okay, so if you're entering, well, you get this payoff here, which is alpha times this coefficient times the indicator of your opponent times beta minus alpha. Okay, so you're going to be cut down by having potentially the other guy in the market. Okay, otherwise you just get 0 if you're staying outside. Well, you also got the epsilons, and guess what? They're going to be I at extreme value. Okay. So we're going to get very nice Logit formulas for the response functions. Okay, so and you see here, we already see it's a game, right? So the other guys, this is a payoff for firm A, and then the decision for firm B that's entering into the utility, or the payoff for firm A. Okay, and you can see here A, alpha, and beta. Well, that's the parameters we want to estimate. You can, in some sense, say, okay, now if I'm in a monopolist, well, that's when dB is equal to 0. What I'm going to get? I'm going to get alpha plus beta minus alpha. So that's beta. So that's kind of the monopoly profits. Okay. Okay, and yeah, that's what we have, right? So you have the monopoly profits, that's A, and then you got duopoly profits at beta. And then see here, this also interacts with different values of X that can differ across different firms. Okay, so so you might want to say this is kind of the size of the firm or something like that. Okay. Okay, so it's not reacting again. Okay, with those utility functions and shocks are going to be a set of Bayesian Nash equilibrium response functions, best response functions. They're going to be logit forms. Okay, so you can see here how the best response of firm B enters into the best response function of firm A. Okay, and if you want to find an equilibrium, well, then it's a set of PA and PB that are mutually best responses. So essentially, you need to find where these two best response functions they are crossing. Okay, and looking with the set of parameters we have here, they're looking like this. So there's actually 3 equilibria in this case. Okay, so you got these two best response functions, and so here you got it for firm A, that's a red one, is a function of the best response of firm B, which is on this axis. And then you got the other one, that's a blue one, that's for the best response for firm B. It's a function of the investment probability or entry probability of firm A. You got that on the other axis. Okay. So there's 3 different equilibria. There's one where the firm A is investing with a very low probability, and firm B is investing with a high probability, and then kind of vice versa. That's where firm A is investing with high probability, and firm B with a low probability. Okay, and then there's this equilibrium in the middle, and so, you know, you can not just plot these best response function and then look at the graphs. You need like an algorithm to solve for these equilibria, or you can try to see if you can estimate these. But you know, then we kind of need that. Yeah. So what I've done here, and this is, I mean, you can do this in very, very simple case. I just substituted one into each other, and you see you get something we'll call or refer to the second order best response function. And so here I substituted, I think this is the best second order best response function for firm A. So this is really, you know, you substitute the best response function of firm B into the best response function of firm A, and then you get like a mapping from choice probabilities for firm A to firm A. Yeah. And then you just need like to find a fixed point on this curve, and this corresponds to these response probabilities for firm A. Okay, so what you could do is if you get this second order best response function, you'll just, you know, you could do successive approximations and to see if this is converging. Okay. Now, okay, so let's just try. So I'm going to start if I'm doing successive approximations, just going to start with some value, say 1.5, right? And then I go like this, and I can trace out that equilibrium. Okay. It's clear that if I start somewhere else, right? For example, if I start here, I'm going to converge to that equilibrium. Okay, so these successive approximations on the player's best response functions, well, they can kind of, you know, give different solutions, and you can see what the problem is. If you know what the result you find depends on whatever starting value you give your algorithm. Okay, and that's I think that's kind of the simplest illustration of what's going to do if you were to solve a game where you say, suppose it's a dynamic game, you have like the player's Bellman equations, and you just, you know, do successive approximations by substituting these into each other over and over again. Well, then you can give very different solutions if there's multiplicity of equilibria, depending on what the starting value of the choice probabilities or value functions are. Okay, and that's not like it's not like that with Harris-Circle, right? There's a unique fixed point. You know, it doesn't matter how you initialize the value function where you search for that. It's a contraction mapping, so you'll find a unique fixed point. Okay, so that's kind of one of the challenges here. Okay, so here in this very simple example, it's easy to devise an algorithm, to do that. You could do some sort of combination of successive approximation and bisection, and I'm not going to go with all the details here, but really what you could do is, you could start here. We know the 3 equilibria, so you can start here. We will find that one, and you can start here, and that will give you that one, and then 2 endpoints you could do bisection. It's going to be trapped in between those 2. You're going to find all these 3 equilibria, and we have like a surefire way of finding all these equilibria in this particular very simple example. Okay. And this is what it says on this slide. Okay. And here's the bisection method. Okay. So now what we want to do is, with this simple model, we want to see, okay, what if we were to estimate these parameters, these alpha and beta? Okay. So we're going to do a little bit of Monte Carlo. Okay. And so here the data generating process is so that the data is generated by a single equilibrium. So we're going to start with that. But in principle, you could have like several different markets where there would be an equilibrium at each market. Okay, we're going to start in the simplest case first, just one market, one equilibrium, and the data is generating from that. So that is, a set of those 2 choice probables, PA and PB, that determine whether or not firm A and B will invest. Okay. Okay, I'll play it 1,000 times. Here's some parameters. Or this is the heterogeneity. So one, firm A is has a little bit larger impact in the market than firm B. So that's how we generate the data. And then given this data, the question is, can we recover what the structural parameters are? Okay, I mean, we can certainly learn and estimate, about these strategies, the P's. That will kind of be a little bit like the CCP estimation, right? But then we want to go like a step further and see, okay, could we learn about the parameters and the payoff functions from all these data? Okay, so we might want to do maximum likelihood. Okay, so we can do that, right? Because we know what the best responses or the choice probabilities of these firms are. These are functions of these structural parameters. You change, the structural parameters, alpha and beta, and then the equilibrium is going to change, right? And so we can write up, standard discrete choice likelihood, indicator for firm A making the investments times the probability that is doing so, the opposite case, and you got the contribution for firm B as well. Okay, all this stuff here is a function of the structural parameters. Now, what are these guys? Well, these are actually the solutions to the set of Bayesian Nash equilibrium equations here. So these are the best response functions that you look at before. Okay, so I mean, these P's here, these functions of the parameters need to be solutions to the game, right? And these solutions, well, they depend on or equilibria, they depend on the structural parameters. So we can move those things around, and then we see, okay, can we fit the data? So here's how you would do that, for example, with the nested fixed point algorithm, okay? And now, okay, you have to have in the back of your mind, you're thinking about like solving a dynamic game, and there'll be like best response functions that have state variables and so on, right? Okay, but the principle is kind of the same, except that solving for those equilibria is going to be a little bit harder, okay? Anyway, so what we do is we do, the outer loop, like in here at soccer, right? You search over the parameters, and then in order to maximize the likelihood function in the inner loop, well, you need to not solve a set of Bellman equations, but you need to solve this equilibrium. Okay, so for a given value of your structural parameters, you need to solve for all the equilibrium. Okay, Has to be all the equilibria, right? Because these are all potentially solutions to the to the game, right? Okay, and let's just denote all those different solutions, one with a subscript or superscript k, to say, okay, there could potentially be more than one equilibrium. In our case, it's going to be 3. Okay, sometimes there's a unique equilibrium. This depends on parameters. I mean, for example, if there's 0 dependence on whether the other guy is in the market, well, you have a unique equilibrium. Okay, it's not very contestable. Okay, so what we do is then we choose the equilibrium that gives the highest likelihood. Okay, I mean, you saw on the graph, right? There is many different combinations for a given set of parameters. There's many different combinations of the choice probabilities. Each of these choice probabilities is going to imply a different likelihood. So if we observe in the data that, firm B is investing all the time, well, it's probably this equilibrium here, right? Whereas if we observe in the data that firm A is investing all the time, well, it's probably this one down here, right? So we can also maximize the likelihood over these different equilibria. Okay, so that's kind of what is going on with the nested fixed point algorithm. Okay, so let's look at the likelihood. Okay, so here's an example from the likelihood function for an equilibrium that was generated by equilibrium number 1. So that's the equilibrium where firm 1 is doing very little investment, where firm 2 is doing all the investment. Okay, and we can see this, like here's the true value. And here's the maximum likelihood estimate. It's kind of, at the top of the likelihood. And we were able to uncover that parameter. That looks pretty good. Okay. You see, let's say fancy contour plots and everything, but you see this is the top of the likelihood. Okay. So it looks pretty easy, right? Let's look at what if the data was generated from equilibrium number 2. Okay. Now you see some action here in the likelihood, and you might wonder what is going on here. Okay, so this is this little bit of this cliff, right? And see what happens is if you just change parameters just a little bit, then there's a discrete jump in the likelihood downwards. Okay. So what could be going on here? Well, see. If I change parameters just a little bit so that suddenly there's an equilibrium that just disappears from the solution, well, I can't use that, and it's not going to be there, right? And I can't use that to explain the data. So suppose that equilibrium where where one of the firms is doing all the investments, is just disappearing from that equilibrium, and you only have the one where it's the other firm that's doing all the investment. Well, the likelihood is going to drop dramatically, right? So that's what's going on here. And you see the same thing for equilibrium number 3. And see what is going on. If you go a little bit back here and look at the slides, let's take a look at this one here. So at the true value, this is what it looks like, okay? But if I change alpha or beta just a little bit, it's going to move these two curves. And you see what happens down here if I move the curves a little bit. Well, these two equilibria is just going to disappear. And there's a unique equilibrium, this one up here. So if the data is generated from either this equilibrium or that equilibrium, well, the likelihood is going to drop because we can only use these choice probabilities up here to put into the likelihood, okay? Because these two equilibria, they just don't exist. So at this set of parameters, so they cannot be in the likelihood. Okay, so you see the challenges, okay? So what are we going to do? Well, we can do a little bit of Monte Carlo. The first case, we do the nested fixed point algorithm with the equilibrium number 1. Okay. True value of alpha is 5. It looks pretty good. True value of beta is minus 11. It looks pretty good. And here the implied investment probabilities also looks pretty good. That's for the nested fixed point algorithm. Okay, and these cases, actually even for this case where you have multiple equilibria, we were actually able to uncover the true parameters, with some noise, of course. It's data, right? So it looks pretty good. So the only challenge is, if you want to do the nested fixed point algorithm here, what we see is the objective function is nasty, right? So you can't use a gradient-based method. So I've been talking all week about how cool it is to get, used to differentiated gradient-based methods, because it's just going to make your problem all the more easier. Quadratic convergence and so on. You can't do that here, okay? You need another option. So, but we were able to just within MATLAB in this simple model to do, F-min search and another mean, okay? So gradient-free method. But you can see it's going to be more nasty to try to see if you can maximize this likelihood function, even for this ridiculously simple model, okay? So this is just to illustrate some of the challenges that there are in estimation of games. Now, alternatively, what we could do is we could, I don't know, didn't I write up that? Oh yeah, here it is. So here's the impact formulation. So you maximize, now again, the same likelihood, but now instead of maximizing with respect to alpha and beta and resolving for the equilibrium every time, like you would do with a nested fixed point algorithm, what you search over is, the structure parameters and then the model solution, which is going to be PA and PB, then imposing the spatial Nash equilibrium constraints as constraints and do a constraint optimization instead. Now that may actually be, everything here is nice and smooth. There's no kinks or anything that's here. These equilibria just have to be there, right? It's not like they just have to be imposed as constraints, and they only actually need to hold at the end, okay? When parameters are converged. Okay, so here's what we get from equilibrium 1, looks good. Equilibrium number 2 looks good, and equilibrium number 3 actually also looks pretty okay. Now, what I did with MPEG here is, what we can do is we can see, we want to have these parameters here, good starting values, right? Then it's easier. How do I get good starting values for PA and PB? Well, here it's just all the frequencies. How many times did firm A invest? How many times did firm B invest? And then you use those as starting values, okay? That actually gets you close to the true equilibrium in some sense, right? So if the data was generated by equilibrium number 1, well, it's going to say this is going to be small and this is going to be big, and it's going to be true, close to the true value. You have a good starting value, okay? And so perhaps this is part of the secret that you can easily solve this with MPEG in this simple example. Okay. I don't know. So I post this as questions, but I can also just answer them. And it's late in the week, it's early in the morning. Anyway, so the likelihood function for the nested fixed point algorithm, well, that's not really smooth in the parameters. We've seen that, right? That was on the slide. There was a cliff. It's non-differentiable. Okay. The objective function for MPEG, well, is that smooth in the parameters? It actually is. Okay, and I could pull it up, and you will see that it is smooth, even in the case of equilibrium 2 and 3. It may be sensitive to starting parameters. Okay. And this is an issue of local minima. It could be that suppose I just started these CCPs in a completely different place. Maybe I thought they were, data was generated by equilibrium number 1 and not equilibrium number 2, but in fact it was generated by an equilibrium that was far away. Then maybe I could get something, parameters that was consistent with that wrong assumption if I were to initialize the algorithm there. But okay, it works out pretty okay so far. Can we identify the equilibrium that was played in the data? Yeah, it seems like these PA and PB. These are things we can estimate, right? Non-parametrically, we can estimate the PA and PB just simply by the by using the data. We observe how many people there are or how many times that each of the firms are investing and not investing. What about standard theorems for inference? If you were to calculate standard errors, usually we assume we can calculate the derivatives of the derivatives of the objective function, the likelihood function, to get the standard errors. In the second order derivative, you need to invert the Hessian, which is to get the variance covariance matrix. Well, that's going to be a little bit dodgy if it's non-differential. Okay, so that's an issue. Okay, now what you want to take away from this is extremely simple. There's 2 parameters and 2 probabilities. And already now we're starting to see some issues. Okay? What would happen if you had the choice probabilities were like a huge function of all the Player-Bellman equations? Yes?
I was wondering, related to the last question, how can you ever be sure that you found all the equilibrium? When you do your dissection.
Excellent question. So there's a question here. How can I be sure that I found all the Markov perfect equilibria if it's a dynamic game, for example? Well, you can't. That's a whole problem. Unless you have a surefire algorithm that traces out all Markov perfect equilibria of this particular dynamic game. Well, here I knew I had an algorithm that could find it. We can show the 3 equilibria, and I just know I can trace it out by the combination of successive approximations and bisections. Okay, so here I'm in short ground. But in dynamic games, well, you can't be sure, right?
So you're doing bisection because it's 3 and not 7.
Yeah, that's why I'm doing it that way. Yes. Okay. Yes.
This idea of equilibrium sort of going away, it seems sort of similar to like the trembling hand equilibrium. I guess how should we think about these things? Like if you think of like sort of equilibriums and counterfactuals, for example, like should we think of things which are very sensitive to sort of model parameters as like, should we rule those out in some sense? Or?
Okay. Now here you have 3 equilibria. Okay. And so you change parameter. And then some equilibria is just disappearing. How to think about that? Well, and in dynamic games, it's even worse. Frieder's going to show you have 1.5 billion equilibria in that model. Okay. And so there's a lot of philosophical questions. Maybe I should not go into that due to time, but we could talk about that. How do all these firms coordinate on all these different equilibria? Can they learn how to play them and so on? Okay. So, but I should probably move on. That's a long discussion. Okay, so we're going to move on here with the case with multiple markets. Okay, so now the heterogeneity, there's going to be heterogeneity in these values X that determines which equilibrium or the type of the 2 firms. Okay. Okay, so we have 25 different types of firms or different markets, and we're just gonna let X, M, and XA vary to see how is these choice probabilities changing across the different firms. Okay, now before they were 2 identical firms, now we can have different types of firms. It could be you know, small firms and big firms, and they all have different choice probabilities that depend on these X's too. Okay, and so, well, in each of the markets, it's still going to be just these two firms. It's just they have a different combinations of XA and XB. Okay. That could give rise to a different number of equilibria in each of the different markets, and could potentially also have different equilibria in different markets. We're going to use the same structural parameters, alpha and beta, all the way through. And then for each market, we're going to solve for all the equilibria in each of the market. And they'll see here, this is most 3 equilibrium in each of the different markets. So here, for the different combinations of XA and XB, well, here we can calculate the number of equilibria. You can see in some markets where you know, say XB is very small relative to XA. Well, then you don't have to care so much about the other guy being there. So there's going to be unique equilibrium. You pretty much just pay attention to yourself. Okay? But in this kind of more contestable case, there's going to be multiple equilibria. And across the different markets, there's going to be some heterogeneity in that. So how do you estimate that model with multiple markets? Well, then you do the same thing with maximum likelihood as before, maximize the likelihood function. Now this just like a response or an equilibrium that's specific to each market. So we just mark them with subscript m, okay, the PMs. Okay, and you do that, you maximize that over or the equilibrium over the structural parameters I think this should be like say outer loop, right? So your the maximization is done outside, and then the inside you calculate the solution of the model. And now there's just more, because now there's a solution at each of the different markets, and so you need to solve for one for each market. Okay, and there could be potential multiple solutions. You need to find all of them if you want to do the nested fixed point algorithm. Okay, and then again we choose the equilibrium, the indicator of the equilibrium for each of these different markets that maximize the log of the likelihood, such that you still have that there's solutions to the game. Okay. Now that's NFXP. And you already see now you need, even as a simple model, now we need to solve the model more times, right? Find more equilibrium. So you can also do MPEG. MPEG does not explicitly solve the Bayesian-Nash equilibrium equation to find all the equilibria at each market for every trial value of parameters. It just has to be an equilibrium at the end, and it needs to maximize the likelihood, including searching over the optimal selection of equilibrium in some sense. The equilibrium that was most important with the data. Okay. So both of these approaches, well, they're both implementing the same estimator. It's maximum likelihood. It's just two different algorithms. So here's a little bit more of Monte Carlo. So here, what do we get? True value is 5. We're doing NFXP, and yeah, I should probably change the number of bins, but bottom line is we're kind of in the ballpark, right? NFXP is tracing it out, even though we're allowing for actually different equilibria being played in different markets. So it's completely random in the data generating process which equilibrium was played in each of these different markets. We could have assumed that it was a particular one, but here it's different. Okay? And we can also get beta. So now there's not like a graph for each equilibrium, because they're just randomly generated. Okay, you got the for MPEG-2, it kind of works. Sometimes it doesn't converge. And here I'm only showing things where the equilibrium is actually where the equilibrium conditions hold. So I'm not just showing something that's converged off to something that's just not a solution, right? These are all solutions. So this guy, this one out here and these ones out here, well, these are just due to local minima, you can say, right? It in some sense, it finds a wrong equilibrium. It's not the one that was played in the data. It was a very low likelihood, but it did converge in the sense that there was a local maximum of the likelihood function. Okay, so now let's go. This is the case where you have a small amount of markets and a lot of observations, or 50 observations for each market. Now, if you have more, fewer markets and more data, well, you have more precision to estimate each of these equilibrium selection rules, and it's going to get you closer. So here's NFXP. This is pretty good. Here's NFXP, MPEG. Yeah, so where's the problematic one? I guess the main message here is that if you have, see this more, these are how much the choice probabilities is varying in the case where you have only 50 observations for each market. You see, there's actually a fair degree of, there's this number of a predicted equilibria that is out here that probably is due to wrong equilibrium selection rule or local minimum. But that problem kind of disappears as you get more data, because you get very precise estimates of what the PA and PP are that you have to initialize the algorithm with. Okay, and there's more data kind of disciplines the algorithm too. Okay, so how am I doing with the time? 50? Okay, we're doing okay. Yeah. Okay, so here's a few messages for. We've been looking at NFXP and MPEG, and we looked at in NFXP. Well, we have only 2 parameters in the optimization problem. In MPEG, well, you have 2 plus 2 times the number of markets.
I have to apologize, it was misinformation, so you only have
minus 15 minutes. Yeah, okay. Yeah, I was kind of surprised. Yeah. Okay, yeah. Anyway, we'll make it. So here for MPEG, well, you have the 2 structure parameters, but you also have to estimate the 2 times M probabilities. There's 2 probabilities, and then this M market, they could potentially be different at each of the different markets. So if you want to allow for, these probabilities to be different across markets, well, you have to estimate all of them. Okay. So now, if it was not 2, but like say the best responses from some dynamic programming model, and there's a bunch of different grid points, it would be much more than 2. It would be like the size of the state space by the number of plates, okay, and then by the number of markets. So this is a little bit more expensive if you have multiple markets. But then, for NFXP, well, you need to find all the different macro equilibria. That's kind of the that's a difficulty here, and can we really do that? For MPEG, well, we have problems with local minima when you have many different markets, because now you're slicing, given a sample size, you're kind of slicing it across different markets. You don't have at each of the separate markets as many observations to identify or estimate precisely these choice probabilities. Okay. Okay, and here's a disclaimer. There's people that are much better at making constrained optimization solvers work than I am. I was just using MATLAB and FMIN Anc, okay? And that could be there are better at tracing out and really finding the unique maximum of the likelihood function subject to all those constraints. So this, this software called Ample and solvers like Nitro that might be more powerful. But I've just done the MATLAB implementation. Yeah.
So is this feasible where, for
When it's what? Well, we don't have actually, so that's a good question. So is this feasible when the equilibrium is not a closed form solution? Well, we don't have a closed form solution here. We need to use this algorithm, which is the combination of successive approximations and bisections. Just think of some algorithm is trying to solve that. Here, it happened to be the case that that algorithm always find any equilibrium that there is in the model. But it's not always like that, right? Sometimes you just have an algorithm that can find some equilibria or just find the nearest one you started at, okay? And then NFXP is really going to be challenged, right? If you would, say, if you would trying to use the algorithm of successive approximations in the inner loop, you search your parameters, you want to find the equilibrium for every value of the likelihood. You do just a successive approximation starting off wherever you estimated from the data that was the equilibrium, but that could converge to a wrong one, right? So if you're using that as your fixed point algorithm or your inner solution algorithm, then NFXP is not that good, right? And so here what I'm illustrating is actually something that you can't really do with most models. You can't just use we don't have that algorithm. Fia's going to show you an algorithm that could do it for a particular class of games, dynamic directional games, find all marker perfect equilibrium. But in general, we don't have those types of methods. So that's why, that's what you guys you're the future, right? You figure it out. Okay, fortunately, we have some very good methods too, that is more relying on the data. And I think we've talked about it during the week. Like CCP type of estimators in the spirit of what Bob Miller was also, talking about. You estimate those CCPs and you use, once those are identified, you hold that fixed and then you basically maximize some pseudo likelihood or whatever objective function you're using. Okay, so here's the idea. So here's the constraint optimization problem. And then let's call the solutions of the parameters and true equilibria for the same thing as there are, just with a star. So PA star and PB star. Suppose that we knew these, how could we just recover the true structural parameters? Okay. Well, we could just substitute that in and then hold those functions fixed and then only vary these and see if that's working. This is idea number one. Okay, so well, there's several different ways you could do it. One would be to simply solve the Bayesian-Nash equilibriums for those solutions, those parameters alpha and beta, holding fixed on both sides of the Bayesian-Nash equilibrium equations, whatever we have fixed the equilibrium values to be, okay? So these could be, for example, estimated from the data and see if you can back out the structural parameters. It may be not that there is a solution to this problem, okay? But maybe you could get close. Here's another idea. You can maximize, say, the log of this pseudo likelihood, where you keep fixed those alpha, those choice probabilities for firm A and firm B that you could potentially estimate from the data. It's a little bit like a pseudo likelihood estimator based on the Hartz-Miller inversion if you go to the dynamic games. Okay. Okay. Now, of course, you need to estimate these PA and PB. You don't know the true ones, so that's what we can do with the data. Okay. So that's feasible, and it's kind of easy. There's no solution of any equilibria, right? It's just you were just holding those fixed, and then we are substituting in the best response functions, and then those best response functions here. Well, this is PA, right? Or PB, and this PA implied by the best responses, holding fixed those choice probabilities that we estimated constant, and then for the parameters, and we just find those that are most important with the data. Okay. And then we can estimate those by, say, simple frequency estimator in this case. Okay. See, there may be, I think I said that these could not just be recovered if you were using idea number one, just solving those equations. They may not be just solutions to this. Okay, but you can also say in another way, if you maximize with this nested pseudo likelihood or with the CCP type of estimator, where you're maximizing this guy here, holding fixed the choice probabilities at the estimated frequencies, well, you're going to get a set of estimates. Okay, and if you take that set of estimates and put it right back in and check, does the equilibrium conditions hold? Yeah, well, in theory, it's going to hold in the limit as n go to infinity. And if the data was generated from this model and, we were able to get it, but in finite samples, it's not going to hold. Okay, so you would be able to see, differences, that there will be residuals to these equations. So then the obvious idea is okay, now this may be just due to finite sample bias. Why don't we just update these estimates with something that we have estimated that's implied by the model where we impose more structure? That's the idea of, equilibria and mirror, that they're kind of updating those choice probabilities, imposing more and more structure from the model. And that turned out to be a very good idea in single agent models. Okay, so you can also do, there's also like these squares estimators. Here's one by Pessendorfer and Smink-Dengler. I'm going to skip that. I'm just going to, show you a little bit of Monte Carlo of how nice this is doing with the two-step pseudo maximum likelihood. Okay, so we still have the problem with multiple equilibrium. We can kind of back out the true parameters. Okay. The problem here is now we're getting a less efficient estimator because we have to estimate all these choice probabilities. We have these additional parameters that we're estimating, and we're not imposing the entire structure from the model. So this is inefficient, and there's Pecos, Ostrowski, and Berry that show that these can be really lead to big biases in finite samples. Here's a very simple case. So it's not so hard to estimate two numbers out of a bunch of data. But if you're estimating like a whole function of CCPs, well, then it can be more prone to small sample bias. Okay, so this was for equilibrium number one. Equilibrium number two, that was the one that was creating some problems before, and you don't have any problems here. It's just, it's just working. The problem is the finite sample bias. Okay. Okay, so now you can deal with this finite sample bias by using this sequential updating of the choice probabilities. Okay, so you estimate, say you start with estimating an initial set of estimates from the data. Okay, just for example, a frequency estimator. Okay, that's step one. Okay, we'll put here the K, I think that we call that the number of steps. Okay, not to be confused with the number of equilibria I had previously. Okay, and then what you do is you find the structural parameters. So K now it's the first set of structural parameters. As the argument that maximizes the pseudo likelihood, this is going to be just equal to the two-step pseudo maximum likelihood estimator we talked about before. Okay. Now, then once you got those estimates, well, you can predict from the model what would the best response functions be, or the best response be to those choice probabilities we estimated, if you index the model at the estimated parameters. That's imposing a little bit more structure from the model. Okay, that gives you this a second step, and then the idea is you can just use those as the initialization for that step. Okay, so it's like instead of using the non-parametric estimates of the CCPs, you use those that are implied by the model you estimated with the two-step pseudo maximum likelihood estimator. And for single agent models, we know from Gaviria Mira 2002 Econometrica, they have this cool paper. It's called Swapping the Nested Fixed Point Algorithm. That's going to work beautifully for single agent models. It's going to, if you iterate more and more and more, it's going to converge to maximum likelihood. So it's going to essentially implement the maximum likelihood estimate. And it's also asymptotically efficient for a given number of iterations. So that's pretty cool. The problem is now we have this issue with convergence, right? I mean, remember what's going on when we're iterating on this best response function? Yeah, sometimes we go in one direction and sometimes we go in another direction, because this is exactly these functions here, right? That we had here. Oh, far away. Okay, sometimes, you know, an iteration is going to, you know, decrease. Sometimes it's going to increase. Okay, is it getting closer to the true value? Well, not necessarily. Okay, that's kind of one of the problems. If you have multiplicity of equilibria and some of them are, you know, unstable, you can potentially get further away from the solution and get worse estimates than you had with the two-step estimator. So let's do a little bit of Monte Carlo and see how is the nested pseudo likelihood estimator, you know, doing. Okay, so we looked at the two-step, that was all right. Okay, here's the method. Okay, and for the NPL for equilibrium number one, it was actually not doing that bad. Okay, okay, maybe because we were starting very close to the solution, and that equilibrium was so separated from the other ones, we're not really in the ballpark of, you know, moving away from it. You start a little bit to the right, well, it's a stable equilibrium, you move back. Okay, you still start a little bit to the left, well, a stable equilibrium, you kind of move to the right, closer to the solution. But what happens when we go to, what is this? Probably just close. You go to equilibrium number two. Here's the alphas you're going to estimate. It's just, you know, often it's not really converging. I'm just plotting stuff here. Your choice probability is clustered across different solutions, and it's just a mess. Okay, it just doesn't work. Even in this very simple example. Yes. Okay. So what we saw here was that if we're looking at the equilibrium number one, it kind of looks nice. Okay. Now we start to look at equilibrium number two. Remember, that was the one in the middle. It's actually an unstable equilibrium. So if you get, even if you get an equilibrium that is right, you know, epsilon to the right of it, it's just going to diverge from it. Okay. So, I mean, maybe it's not so surprising that that it's not nailing that equilibrium. But what about equilibrium number three? Is that always working because it is a stable equilibrium? Well, see, the problem is sometimes you just get to the wrong side of the unstable equilibrium. You've got to converge to equilibrium number one. Okay, so you get these two different predictions from the model and the structural parameters where there's some cases, well, they actually look pretty okay, but they're predicting different things. Okay, so actually, I think I'm already ready to conclude. So the nested fixed point impact implementations of the maximum likelihood estimator. Well, that's statistically efficient. It's imposing all the structure of the model, and you know, it's maximum likelihood. But it can be computational a little bit daunting. You know, in one case, in MPAC, well, you need to impose all these constraints and potentially solve a high-dimensional constraint optimization problem, at least in models that are somewhat bigger than this. Okay, where you have many different constraints, especially in dynamic physics. Okay, and if you have many different markets and you have like, you know, your data set is big and you want to do one, you know, in many different markets, well, then you have even more constraints. Well, with NFXP on the other hand, well, you need to find an algorithm that can find all the equilibria that were potentially played out at all the different markets. But remember, it's not like you have to solve the model m times. It's actually for a given set of parameters. There's just one equilibrium or three. Okay, so it's just these three solutions. And so we can reuse these solutions. So the two-set estimates are computationally very fast. No algorithm to solve for the equilibrium. Okay. That can really make a difference, and it's also, but it's kind of inefficient, and it can be biased in small samples. Then the idea was, you know, the nested pseudo likelihood idea of updating the CCPs that would really kind of bridge the gap. Oh, okay. What I just said was really on the slide. NFXP, you know, that's statistically efficient, but it can be computational hard because either you need to solve constraint optimization problem, or you need to find all the equilibria of the model. Okay, you need algorithms for that. The two-step estimators, they're computationally fast because there's no such, you know, requirement. You just, you know, go out and estimate the CCPs, you throw them into your best response function, you have your objective function, whether it's least squares or a pseudo likelihood. But there may be bias in small samples if you don't really accurately estimate those CCPs. Okay. The nested pseudo likelihood by a Gabiria and Muir, 2007, that's the one about games. Well, that should bridge this big gap, but we've seen it can, at least for this simple static game, be very unstable when estimating games with multiple equilibria. Okay, not only when you're in the case where you are trying to trace out an inefficient or no unstable equilibrium number 2, but also for equilibrium number 3 is kind of close by. And certainly it doesn't, you know, converge from anywhere. Okay, so here we potentially have some issues. And then we'll talk about, you know, estimation of dynamic games in just a minute, or mostly about the solutions, because we focus on how to do that at the NFXP. It's kind of established how you do with nested pseudo likelihood. It turns out have these instability problems. So we are trying really to see if we can find all full solution methods to find all macro perfect equilibria. We're not quite there yet, but estimation of dynamic games, that's interesting, but it's really a challenging computational problems, because you can have, you know, the multiplicity leads to likelihood functions to be discontinuous. We saw that the cliff, right? That's already making the problem more hard. And you also get to just find the optimal, but also give non-standard inference. And then multiplicity of equilibria also leads to kind of indeterminacy problem education issues. Okay, and once we go to dynamic games, this is just amplified by orders of magnitude, because there could just be so many more equilibria. I think that's it.
Thank you very much. Okay, are there any questions first? All right, then thank you very much. So we'll take a 15-minute break and then we'll be back.
Oh, by the way, there is some MATLAB code in the repo that's you know, doing all these graphs that you see here, and you can run them. Let me just quickly give an illustration. Here's the one to run the figures. It's called RunFix. Okay, so it's doing this, and it's implemented all these different estimators. There's also one for Monte Carlo and so on. Okay, you can if you want to just get an idea about these, just conceptually about these different types of estimators, I mean, at least for me, it's helpful to look at other people's code. Maybe not mine, but good luck.